Hi everyone, welcome to my channel. In this video I'm going to cover the concept of the full adder logic circuit, and we'll actually go through the concept, put together a truth table, design a logic circuit, and then I'll show you the actual working logic circuit on a breadboard. The essential function of a computer is the ability to perform arithmetic operations like addition, subtraction, multiplication, and division. All these arithmetic operations are performed in the arithmetic unit of the computer. So this arithmetic unit is going to accept binary data that is stored in memory, and it's going to perform arithmetic operations on this data according to instructions from a control unit. So a control unit is going to tell the arithmetic unit what mathematical operations to perform on data it retrieves from memory. Let's take a look at a block diagram of this concept. Here's a block diagram of the concept of an arithmetic unit, and it consists of the blocks within this dashed border. So you can see here we have two registers, and in between we have some logic circuitry. We're going to call this register the accumulator register, and this register the B register. We have a block here representing memory and a block here representing a control unit. Now, a typical scenario would be that the control unit receives an instruction from memory specifying that a number stored at a particular address needs to be transferred into the B register to be added to the accumulator. So the number is transferred from memory into the B register, and then the B register number and the accumulator number are combined in the logic circuit, and the sum is stored back in the accumulator. So now the new number in the accumulator, that can either remain and wait for yet another arithmetic operation to be performed from another number from the B register, or if it's a final result, that can be then transferred for storage in memory. The reason this register is called the accumulator is that this register accumulates the sums that occur when performing successive additions between new numbers acquired from memory and the previously acquired sum. So now let's look more closely at the process of adding two binary numbers. Now here we have two registers storing two 5-bit binary numbers. This is the accumulator register, and here is the B register. And we want to look closely now at the process of adding these numbers, and we want to keep track of the sum bit and the carry bit. So we'll start at the lowest significant bit, and we have a 1 and a 1, which is going to equal a sum of 0 and produce a carry of 1 into the next bit position. Again, this produces a sum of 0 with a carry bit of 1, which gets carried into the next bit position. In this case, the sum bit is going to be a 1, and the carry bit is going to be a 1. So that carry gets brought over to the next bit position, and in this case we have a sum bit of 1, and it produces a carry bit of 0, and in the last bit position we have a sum bit of 1 again and a carry bit of 0. So you can see here, except for the first position, at each step in the addition of these two 5-bit binary numbers, we are adding 3 bits, an odd bit, an add-in bit and a carry bit from the previous position. And that process duplicates itself for each of these positions. So if we can design a logic circuit that can accommodate the addition of the adjunct bit, it has to account for 3 bits: the adjunct bit, the add-in bit, and the carry from the previous position. And it has to produce a sum bit and a carry bit. So once we come up with this logic circuit that can accommodate the adjunct bit, the add-in bit, and the carry from the previous position and produce the sum bit and a carry bit, we can just string those circuits together, similar to how we string together flip-flops to create additional storage for an additional bit. So recall that these blocks here are just flip-flops, and if we want a larger register, we just add another flip-flop. So once we come up with this logic circuit, we can just string them together to accommodate adding any size registers. So now let's summarize this in a block diagram form, and it'll start to become more clear. So here's a block diagram of the concept of adding the addend or B register bits and the adjunct or the accumulator or the A register bits. We're going to have this block diagram here designating a full adder. And you can see for this full adder, it needs to accept a carry in from the previous position. It needs to accept the bit from the addend and the bit from the adjunct. And it needs to produce a carry out bit and, of course, the sum bit. And once we design this circuit, these are just duplicates. It's the exact same circuit, and we would just need one for each bit position depending on how large the 2 registers were that we were trying to add together. So here is one of those blocks that we're calling the full adder, and you can see we need to have this logic circuit in here is going to accept a carry in, an add-in bit, an adjunct bit, and it's going to produce a carry out and a sum bit. So now that we know how we want our full adder to process all these inputs to produce these outputs, we can put together a truth table that will show or summarize the outputs for all possible combinations of inputs. So let's put together that truth table. Here's the truth table that's going to help us design the logic circuit we're going to call a full adder. And I've already filled in all the bits that we're keeping track of. Here are the input bits, which are just every possible combination and progression. And we want to now determine what the 2 outputs are going to be. We have a sum output and we have a C output bit. So when we're adding A register and B register and we have a carry in, the sum is going to be a 0. A carry out is going to be a 0. When we have the A register bit is 0 and the B register bit is 0 and the carry in is 1, the sum will be a 1 and the carry out will be a 0. When we have an A bit of 0, a B bit of 1, and a 0, again the sum will be a 1 and we won't have a carry. The carry is 0. Now we have 0 and a 1 and a carry of 1. So the sum bit will be 0 and it will produce a carry bit of 1. Now we have A1, B0, and a carry of 0. This will be a sum of 1 and a carry of 0. Here we have A bit 1, B bit 0, and a carry of 1. That will produce a sum of 0 and a carry of 1. Here we have an A bit equal to 1, a B bit equal to 1, and a carry in of 0. That will be a 0 with a carry of 1. And finally, we have an A bit 1, a B bit of 1, and a carry bit of 1. That will produce a sum of 1 and a carry of 1. So that summarizes the outputs that we want for our full adder circuit for every possible combination of inputs. Remember, this is the truth table that summarizes the circuit that we want in this block diagram here. That's how we want this circuit to function, and it's summarized in this truth table. So now that we have the truth table, we can come up with a Boolean expression that represents this truth table for the sum output and the carry output. So in this particular case, I'm going to use the sum of products method, and we're going to produce a product term for each of the outputs where the sum is 1, and then they will be ORed together. So the first one here is A0, B0, C. So the sum will equal to, the first term is A0, B0, C. The second term, where the sum is a 1, is A0, B, C0. So we add here A0, B, C0. The next one here is A, B0, C0. So we add that, A, B0, C0. And finally we have A, B, C. A, B, C. So now we need to simplify this expression. None of these terms have two variables in common with any of the other terms, but we can start factoring out. Here we have an A0 that we can factor out. This is B0, C, ORed together with B, C0. And here we can factor out A. So A, this is B0, C0, ORed together with B, C. Now, do you recognize anything with these expressions? This here is the expression for an exclusive OR gate. This is an expression for an exclusive NOR gate. So we can simplify that by A not and B exclusive OR C, and that's ORed together with A and B exclusive NOR C. If we say X is equal to B exclusive OR C, and simplify this expression further, we have A0 X ORed together with A X0. And we just recognized this expression up here as an exclusive OR gate. So S is equal to A exclusive OR x. And if we fill in, we substitute what x is, this becomes A exclusive OR with B exclusive OR C. That's what the sum output will equal. Now we need to produce the Boolean expression from the truth table for the carry out. So here's the carry out is equal to 1, where we have A naught B C. So carry out is equal to A naught B C, or together with, next one we have is here, which is A B naught C, A B naught C, or together with this one here, we have A B C naught. A B C naught, and then the final term is A B C. We have A B C. Now we need to simplify this expression. Now to simplify this, we can use a little trick. Remember one of the theorems where x ORed with x is equal to x. So we can add an ABC term for each of these two terms without changing this expression. So this can become C out equal to A naught B C, or together with A B C, or together with A B naught C, or together with A B C. And then of course we have this, I'm running out of room here, A B C naught, and this final A B C. And that's because we can add as many x's to an OR gate Remember, an OR gate produces a 1 when any one or both of the inputs is 1. So it doesn't matter what x is. If we tie these two together, together like that, x will produce x. So now we can start simplifying. We have BC we can factor out. We have A naught A, and here we can factor out AC, and we have B naught B, and then this last term here we can factor out, let's see, AB, and we have C naught C. Now these, if you have A ORed with A naught, that's equal to 1. If you recall, if you have an OR gate, and if this is, in this case, this was A, and then we fed into the other side through an inverter, so this was A naught. Depending, no matter what A was, the other would be the opposite. So if this was 0, this would be a 1, and an OR gate produces a 1 output when there's a 1 on any of the inputs. So this would be a 1, this is a 1, and this is a 1. So the C out is equal to BC, or together with AC, or together with AB. And that can't be simplified any further. So that's 3 AND gates, and they get ORed together with a 3-input OR gate. So there's 3 2-input AND gates, and they get ORed into a 3-input OR gate. So based on this equation for the sum out, we know that we have an exclusive OR gate. That's S output. We're going to have an A input, so that's A, and the other input is the other exclusive OR gate. So we have another exclusive OR gate that feeds this exclusive OR gate, and this input here is B, and this input here is Cn. So this is B, this is Cn, and this is B, exclusive OR Cn. So now we just need to figure out the circuit for the Boolean expression here that's for the C output, and add that onto this circuit. So we know we need 3 AND gates, 1, 2, and 3, and a 3-input OR gate that they feed into. That's C out. So now we have the C in, say C in, to here, and we know that one of these has to be a B and a C, so we have C in here, and his B come down to here. So that's this one, and we have AC and AB. So this B can be extended to here, and this would be the A then. So we have an A that we can bring down to here, and we also have an A here and a C in, which goes to here. So this is the full adder, and this is the circuit that we duplicate for each bit position in the registers when we're adding the bits in an accumulator register and the B register. Each bit position will have one of these full adders to accommodate the A and B and the C, the carry in, to produce a sum and a carry out. So this is a full adder circuit made with individual logic gates, but a more practical use would be in a larger integrated package. And if we look in here in this old TTL data book, right here we have a 4-bit binary full adder with fast carry, and this has the inputs for 2 4-bit binary numbers along with the full adder circuitry for each bit position. So all in one package you can add 2 4-bit binary numbers, and it will produce the correct output sum values and the carry. And you can see here the circuit layout, and here's the truth table for that circuit. So to show that this worked, I went ahead and built this circuit up on a breadboard with individual gates. So we can see when we add 2 bits and a carry, we get the correct sum and carry output. Let's take a look at that. So this is the schematic, and here's the circuit on the Heathkit Digital Design Experimenter. So here I have the 2 registers, the 2 inputs. We have an A and B input and a carry in, and then I have the sum bit and the carry out. So this should follow the truth table that we put together. So if all the inputs are 0, we should have 0 out, and we do. If we have a carry in of 1, we should have a sum of 1, and we do. Then if we have any one of these bit inputs from a register, we'll have a sum, and we do. And if we have any one of these registers that has a 1 bit and we have a carry, the sum will be 0, but we'll have a carry of 1. And that's correct. And the other combination is when we have 2 bits that are 1, that are the inputs for the 2 from the 2 registers, and a carry of 1, which is a 1 and a 1. So this is all working correctly. So that's the full adder circuit, and you just string those together. If you want to start adding larger and larger registers, you have to have a full adder for each bit position to add the numbers in the bits in each register. And with that basic building block, we can start subtracting numbers too, and multiplying and dividing, and that is where the power of the computer comes from, is the ability to do all these arithmetic operations very quickly. So I hope you found this video interesting. Please like, subscribe, and/or comment, and thanks for watching.